This is discussion of strand G for the OCR data analysis controlled assessment task. Okay, so across the top of the screen you basically have a simplified version of what the official mark scheme says about how to get the various different marks, and a suggested sequence of things you should do is something along these lines. Remember, what we're trying to do is to establish whether or not your experiment agrees with your hypothesis, how the science relates to that, so whether or not you'd expect it to agree with the hypothesis based on the science, and also to talk about any more data you could take that might give you more confidence in your hypothesis. So in order to do that, we need to state the hypothesis, and that is written on the exam board OCR sheet. So the first thing you do is to copy that down as your stated hypothesis. Then you describe the trend shown by your results in as much detail as you can, and then you compare the two, so you're seeing whether or not they agree. You then link in the scientific knowledge to your trend and its hypothesis, so how does what you expect to happen relate to what you have seen happen, and finally you talk about the extra data. So here's how to do that then. First of all, describing your trend. Well, as a minimum, your description of your trend should link the independent variable in your experiment with the dependent variable. So in this case we've got our familiar example we've used before, which is a variation of drop time with drop height, dropping a ball bearing from different heights and seeing how it affects the drop time. So in this case, as drop height increases, drop time increases as well. So this is sort of the minimum level of detail in the description you would expect. And remember here, the independent variable is drop height, that's the one that you're controlling in this experiment, and the dependent variable is drop time. So you'll need to make sure you're clear on which variable is which for your experiment so you can describe the trend properly. Well, that's the minimum level of detail. We can actually do better than that. We can sort of describe the change in the trend as we go through. So as drop height increases, drop time increases. The drop time increases rapidly with drop height at low values. You can see that on the graph, that the change in drop time is big for a relatively small change in drop height to start with. That's shown on the graph by having a steep line. And as we get up to higher values of drop height, the drop time still increasing, but it's not increasing as much. Okay, so I've referenced in this description which values I'm talking about. So at low values of drop height, 0 to 100 centimeters, the increase is quite rapid, and at high values of drop height, 150 to 200, the increase is much more gradual. So that's a much more detailed description than just saying as one increases, the other increases. There are also a couple of special kind of trends that you should be aware of, the first of which is a direct proportion. So any trend line which is a straight line going through the origin, or very close to the origin, because unlikely it'll be completely through it, can be said to be directly proportional. So in this case, if these were the results we got from our drop height experiment, we would say that drop time is directly proportional to drop height, as the line of best fit is a straight line going through the origin. So if that's what your data shows, you should try and use the words direct proportion as well if it's relevant. And then, ridiculous as it would be for the results to be this from this experiment, I'm just using the experiment as an example. You wouldn't get results like this from dropping a ball bearing. But if you had the case where you get an inverse proportion, then the way you check for inverse proportion is that if you halve the value of the dependent variable, it will double the value of the independent variable. Okay, so looking at this, what we can see is we'll just take some points on the graph to show this, and this will make it a lot clearer. So we start with our point here highlighted in green of a drop height of 50 centimeters and a drop time of 0.6 seconds. Okay, if this graph shows an inverse proportion, then when we double the drop height, our independent variable, to 100, we halve the drop time to 0.3. So that works. Okay, if you're checking for inverse proportion, you should really check two separate points just to make sure it's not a coincidence. So we should check again. If we take our 100 drop height and double it again to 200, then we should go down to a drop time of 0.15, and sure enough, that's what we get here. So if you're trying to show that you've got an inverse proportion, it's worth checking those points like that, okay, and showing the doubling and halving occurring, okay, with doubling with the independent variable and halving of the dependent variable as you go along. So those are some ways you can describe your trends. So if you want to pause the video now and have a go at describing the trends shown in these graphs, and then we'll discuss those descriptions in a sec. Okay, so first graph then we've got is time and speed on the axes. Remember, the independent variable is always on the horizontal axis, so we know which one is which from the graph. So in this experiment, no idea what it is, but we're just describing the experiment. As time increases, speed increases. You can see they go up together. Speed increases gradually with time for small values of time. We've got a shallow curve to start with here, and more rapidly with time at a greater value of time. It gets steeper. The trend line I haven't put on here, but you can see where it would go. Right, so you can see that description is relevant. For the second one, well, this time we've got distance as our independent variable and force as our dependent variable, and here, as distance increases, force decreases. And it's certainly not an inverse proportion because we haven't got this halving going on. But we could comment to give more detail on the fact that the rate of decrease is fairly steady because it's a straight line. Okay, so the rate of decrease of force is fairly constant across all values of distance. That's what we get from our straight line relation here. And finally, we have one of our special cases. In this case, it's the experiment is applying a force to a spring, which is one you've probably all done in Key Stage 3. And we're saying here that extension is directly proportional to force, as the trend shows a straight line through the origin. Okay, so there's our three descriptions of trends, and you should aim to describe your trend in as much detail as you can. Okay, so once you've done that, you need to compare your trend with your hypothesis. Okay, and the possible forms the hypothesis can take is that either it will state something like the independent variable affects the dependent variable, or the dependent variable depends on the independent variable. And they both mean the same thing, really, that there's an effect from one on the other. And there's only really two types of results graphs that would disagree with that. The first of which is that your points are randomly scattered all over the place. And if they're randomly scattered all over the place, that suggests that the independent variable doesn't affect the dependent variable. You've changed one thing and it's not really had any effect. The points are just randomly scattered about. It's likely they're randomly scattered about because you haven't controlled something you're supposed to have controlled. Think about your control variables for your experiment. Something else must be varying to cause this, because it doesn't look like there's any pattern relating the dependent variable to the independent variable. Okay, and the other situation in which you can have the dependent variable not affected by the independent variable is a horizontal line, right? So you're changing the independent variable and it's having no effect whatsoever on the dependent variable. Okay, so in those two situations you would say that your results would disagree with the hypothesis. Okay, of that form. Pretty much every other situation will agree with those two forms of hypothesis. I mean, if the hypothesis is more specific, if the hypothesis says something like the independent variable increases and the dependent variable decreases, and your results don't agree with that, then obviously you've got to say that too, right? But the hypotheses tend to be of this form. They're not being specific, they're just saying one variable affects the other. Okay, so it's unlikely that you're going to get results that are going to be randomly scattered or are going to show no relation whatsoever. It's possible, but it would be much harder to discuss if that was the case, and the experiment would be kind of pointless to do. So, but do say if the results disagree with the hypothesis, and you've got to attempt to come up with some sort of scientific explanation as to why. So you need to watch the relevant science video for your data analysis task, which will be in the playlist as well. Okay, so let's say we have got results that do agree with the hypothesis. In other words, there is a trend, there is a relationship that we can see between the independent and the dependent variable. You can still change the hypothesis and make it better. Okay, so you shouldn't just say yes, the hypothesis is correct. You need to improve on the detail, and the way you do that is to use your detailed trend descriptions. So where you've got more detail in your trend, use that as your new hypothesis. Okay, so write the new hypothesis like this: show how the dependent variable changes with the independent variable. As one increases, does the other one decrease or increase? And also remember to describe how quickly the change takes place, just like we did before. Okay, is it rapid at low values and gradual at high values, or vice versa? And don't be afraid to use the other two specific trends that we talked about. If it's directly proportional, say it's directly proportional. Okay, if it's inversely proportional, say it's inversely proportional. Okay, and demonstrate how you know that. Okay, so have a try at this then. So we'll take our spring results from before, so you hopefully remember what the trend description was. If you don't, you can have another go. And I'm going to say that the hypothesis for this experiment that we've been given is the extension of a spring depends on the force applied to it. So pause the video now and see if you can come up with the trend, whether or not it agrees with the hypothesis, and how you would change the hypothesis, okay, to fit better with the results. Right, well, let's see if we can go through that now. So, here's what I've got. So, it is extension is directly proportional to force, as the trend shows a straight line through the origin. So, there's our description of our trend. A statement that says that it agrees with the hypothesis, as the extension does depend on the force applied. And another statement to say, well, we can do better with our hypothesis. We can say, instead of just that the extension depends on the force applied, we can say that the extension of the spring is directly proportional to the force applied to it. And that's the change in the hypothesis we should make. You should note as well that at this point you should try and explain why that makes sense scientifically. So again, for your experiment, at this point you should also insert an explanation that backs up this new hypothesis based on the science. Why do we expect it to be this way? Okay. And the final thing to talk about for the highest marks is what you need to do in terms of taking more data. So basically the idea is that we're increasing our confidence in our conclusion. So that's how sure are we about our trend? Okay. Can we be definite that it's directly proportional? Can we be definite that it's inversely proportional? Can we be definite about the changes that are going on? So there are kind of three basic ways you can do this, so that you could possibly think of more. And the three of them are this. You can increase the range of your independent variable. Alright, so if you measured over a certain range of values to start with, if you measure over a wider range, you would at least have more confidence that your trend continues beyond that range. Because without doing the measurements, we can't really extend the trend forever. So to take our example of our spring, well, eventually, what happens with the spring is it starts to stretch more. So doesn't stay directly proportional. Right, the line starts to curve, and if we take that to its logical conclusion, eventually, if we apply enough force to a spring, it'll break. So we know that that trend can't continue forever, and if we wanted to be certain about how it behaved, we would have to do more measurements. We would have to add more force to our spring to try and see how it extended. And you have to try and apply that to your experiment. So whatever experiment you're doing, can you extend the range of your independent variable to be confident about your trend across a wider range? Second thing we can do is we can take more data points between readings. If, for example, you've got a big space where you're not sure how the trend's behaving, or if you have a point that seems like it's lying off the line, is that actually a real thing going on with your trend? Or if we took some more data points around that, we would see in more detail whether it was. So if you decide to take more data between readings, right? So if you've taken two values of your independent variable, say whatever units 3 and 5, and you decided, well, you need a reading at 4 that you haven't got, then refer to the specific data points on your graph and explain why, right? So if you've got points in your graph that are off the line of best fit, you might want to investigate in more detail around those just to check what's going on there. And if it turns out that those new points you take are on the line of best fit, then you've probably got a good case for saying you have a higher confidence in your trend. And the final thing you can do, and it's a bit of a cop-out this really, because you could always do this, is that you can take more repeats, and more repeats tends to mean more accurate average values. So if you've taken 3 repeats, you could take 4 or 5, but it gets to the point where this is not going to make much difference. I mean, much beyond 5 repeats, you're unlikely to see much difference in your average values. Okay, but the more data you've got in support of your trend, the more confident you can be. So that is theoretically one thing you should do. But if possible, talk about the first two. All right, it's easy to sort of go for that last one because it's easy to explain. But if you're really going to get good marks, you need to explain the first two properly. hopefully that should help you get as many marks as you possibly can on the G strand of the coursework. Do remember to go and watch the science specific video as well, so that you can put the scientific explanations in to back up your trend and hypothesis descriptions.